So at long last, we're ready to start the discussion of Spring WebFlux, which is really the last major part of the class we're going to cover, and how to do reactive programming across the network. And we'll talk about what Spring WebFlux provides that goes above and beyond what was in the earlier versions of Spring, which, as you saw, was Spring WebMVC. That's what we focused on earlier. Now we're going to talk about Spring WebFlux. So what is Spring WebFlux? It's a non-blocking web application framework that allows you to leverage a lot of cores, or as many cores as you have, really, and handle a large number of concurrent connections without requiring a large number of threads. So that's kind of the motivation, a large number of traditional threads. The way that things work should be familiar to you now that we've talked a lot about reactive programming. Requests that come across from a client to a server are handled ideally in an asynchronous, an entirely asynchronous, and entirely lazy manner, which is interesting and also has some quirks in terms of how you figure out where the time is being spent in your program. So as an example, let's say that we're going to make a request from a client to a server to get back a list of flights. Let's say we have a flight booking application or a flight listing application. So, of course, if you request the server to send back the list of flights with normal Spring WebMVC, that'll take a few seconds because you have to go across the network. The server has to go look it up in a database, has to coalesce it into a list, and then send that entire list back to the client. But the cool thing about using it with WebFlux and Fluxes and asynchronous programming, reactive programming, and so on, is that you can get the results back, or start getting the results back much more quickly, and you don't have to block the client or the server. So the whole thing becomes non-blocking if you play your cards right. So one of the consequences of this is a smaller number of threads are required, because we only need to have threads that are actually doing blocking computations or doing computations in general, and we don't have to have the blocking is going to be done off the main thread in a pool of threads, so it doesn't require a large pool of threads. You typically have to have about as many threads in a thread pool as there are cores, plus or minus a few. So when you have I/O-bound operations, remember that that may require the infrastructure to adaptively increase the number of threads. And of course, the way that that's done with Spring, WebFlux, and with Reactor is by using some of the schedules we've talked about, like bounded elastic, which can grow or shrink depending on whether threads are blocking or not. Now, one of the consequences of doing things in this very asynchronous way is there may be a need for so-called non-blocking back pressure. Now, we haven't talked a lot about back pressure. We'll talk more about back pressure in the next couple weeks. But what back pressure does is it allows the consumer or the subscriber to control the event rate so that faster publishers don't overwhelm the subscriber, don't make the subscriber be drowned in a sea of events that are coming to it more quickly than it can deal with. And we'll talk a lot more about that. Now, interesting point to note here. The introduction of Java virtual threads in Java 19 and beyond provides some scalability benefits without requiring non-blocking clients and servers. So you can have things that block. So we'll see when we start looking at some examples. We probably won't get to that today, but we'll definitely get to it on Wednesday. What's really interesting about that is that you can combine virtual threads with WebFlux so that you can end up with having threads from the virtual thread mechanism, and then combine that with the reactive programming. So you get this really cool kind of combination of the two. Now, so that was all discussions about concurrency. Let's talk about communication. So the way that communication works under the hood is by using the reactive types we've come to know and love from Project Reactor. So things like fluxes and monos can be used to send data back and forth. Now, you can also use other stuff too. You don't have to just rely on fluxes and monos, but it gives you a lot of flexibility in terms of being able to use reactive types. So as you know, the monos give you this sort of 0 or 1 asynchronous behavior, somewhat like an optional completable future, and fluxes give you this kind of 0 to n behavior. And so you can imagine a couple of different examples that could use this. So here's one where we're going to have a method that's going to be part of a controller that's going to take in a departure airport and an arrival airport, and then give you back departure dates as a flux that could be used to give people a user interface on the client side to decide when they want to book flights, for example. And that would come back as a flux. So we'll talk more about how that works in a second. Likewise, you might have another service for doing some kind of exchange rate behavior. So you might want to find out what's the current currency mapping from euros to pounds or dollars to yen or something like that. And again, you can have this be done in an asynchronous way by using a mono. There are a very rich set of operators, you're already familiar with this, that are part of the ReactiveX vocabulary of operators. These would include things like we talked about, like map and flat map and so on. And they're both available for RxJava and Project Reactor. We're focusing on Project Reactor because that's what comes integrated out of the box with WebFlux. So what makes these reactive types, especially fluxes, interesting and powerful is that they can be streamed element by element. So you might say, I would like to get the list of airports, and it'll give you back a flux of airports. And what's useful about that is you don't have to wait for all the elements to be assembled on the server side before the elements are streamed back, before the various things are streamed back to the client. So as a consequence, you can make your clients more responsive because as the data starts to come in, it can be displayed right away rather than waiting for it to all be buffered up and sent back in one fell swoop. For various reasons that are sort of frustrating, Android and its retrofit mechanism doesn't really support fully reactive WebFlux clients, and retrofit actually has some limitations in general, but we're going to see how we can fix that. There's a newer, last couple months, capability that's part of Spring 6 called HTTP interface, and that is very cool. That also doesn't work on Android, but it can work in non-Android environments, and so you'll get a chance to play around with that for the next assignment. You can also use these things called streaming server sent event model. So you can keep a stream open and then send the response back as the data is generated. So you can do something like this, where you're going to have the ability to send back a stream of rates that could be kept live. You know, like let's say you were trying to keep track of currency over time, which may fluctuate minute by minute. You could do something here to return a flux of these things and then keep the stream open. So that's another cool feature that's added with WebFlux. Another nice thing, and this is a little bit dated, this is sort of pre-Java virtual threads, reactive stacks can have better response time and process more requests per second than the traditional platform thread-based non-reactive stacks. So there's an article here that compared the performance of the servlet stack, which is the guy over here on the left, and the reactive stack, which is the guy over here on the right, in terms of various properties, in terms of the latency, and in terms of throughput, and so on. And they found that because of the way that the reactive stack worked, they saw better performance. These things need to be updated, of course, now that we have support for Java virtual threads, and so that comparison would be interesting to see in the brave new world of structured concurrency and Project Loom and so on and so forth. But at least at one point, this was a win. One of the things you have to be very careful about when you start trying to measure performance with reactive programming is the fact that the traditional way of measuring performance, which is to send a request to the server starts a timer, then when the server's done, it sends the result back, you stop the timer, you see how long it took. That doesn't work properly with reactive programming because the server only keeps it for a short time. It just keeps it long enough to send back the flux to the client, and then when the client does the subscribe on, that's what actually pulls the data from the server. And so the server gives you this sort of underestimate of how much time it actually took, because it's not spending much time actually in that call. So we're looking at ways of being able to measure that a little bit more accurately to give better results for our benchmarking. So that's the end of the overview of Spring WebFlux. And you're going to get a chance to play around with this with programming assignment 2C very soon.